Good morning, everyone. Uh, so today, what we will do is we will try to look at the software architecture of a compiler from a very high level. Okay, and then we will also start looking at the syntax analysis phase of the compiler. That also we will study from a high level picture. Okay. So after by the end of today, I will release the second homework and also uh, the first. There's a first phase in the project which is on syntax analysis. To get things going, I will release what you should be doing for this week in the first phase of the project. Okay. So all the details you will get through Moodle. Keep an eye on the Moodle mailing list. All right, so let's get started. Uh, so if you take a compiler, so what the compiler does, it takes a source program and generates machine code equivalent to the source program. And so the first thing is the compiler must recognize before it does this code translation. The first thing it should do is it should recognize whether it's the program that is given to it, if it's a legal program or not. Okay, if it's a just 1 minute, guys. Yeah, so it should recognize if it's a legal program, if it's a legal program or not. The compiler should recognize. Okay. The second thing is, once if it's not a legal program, then it should generate suitable error messages, like what are the problems with the source code that is present, or whether there are any syntax errors, whether there are any semantic errors. That kind of error messages the compiler should give to the user. And if the program is a legal program, then it must generate number one, correct code. Okay. The generated code, the generated machine code should be semantically equivalent to the source code. The second important requirement is it is not only should not only generate correct code, it should generate efficient code. Like for example, if you have written code for a sorting algorithm, then the generated code, if it takes an hour to sort, let's say million numbers, then you don't want to use such a compiler, because the execution efficiency of the generated code is pretty bad. Okay, so the compiler must generate correct code and it must generate efficient code. Okay, so generating correct code is a reasonably easy task, but generating efficient code, that's where the challenge comes. Okay, and of course, no, it has to map, it has to do memory management, like where should, in the process of mapping your source code to the target code, it has to worry about where memory for local variables are allocated, where memory for global variables are allocated. All these things it has to worry about. Okay, and of course the generated executable, it should respect the requirements of the operating system. Okay, because what happens is the generated executable, when we give that program for execution, the operating system loads that program into memory. So if you generate an executable which is not compatible, for example, with the Linux operating system, then the Linux operating system will not be able to execute the program, that is the executable code that is generated. Okay. Similarly, if you want to link your generated object code with other libraries, then you have to respect the format, linker format, etc. So the generated object code, it should respect the operating system and the linker conventions. Okay. In the absence of that, the generated object code cannot be linked and be made ready for execution by the operating system. Okay. So as I said in the last class or before class, there is a in terms of complexity, there is a humongous difference between compilers and assemblers. Okay, mapping assembly code to object code is relatively an easy task, but mapping uh, C code or C++ code into equivalent assembly code or object code, it's a very challenging task. It requires, there's a lot of 30 to 40 years of research went in this in designing this compiler. Okay, so 30 to 40 years of research went in designing this complex piece of software which we call as compiler. All right. Um, and then so if you see, if you kind of take a peek into one step peek into compiler, so a compiler consists of a front end and it consists of a back end. So the front end of the compiler checks for syntactic and semantic correctness of the program. Okay, this is what the front end does. Checks for syntactic and semantic correctness. And if the program is syntactically and semantically well formed, it generates an intermediate representation. Okay, and this intermediate representation is passed to the backend of the compiler, and the backend of the compiler maps this intermediate representation into target assembly code. Okay, so here there are two observations that we have to keep in mind. Number one is that the front end is dependent on the source language. Okay, the front end for a C compiler would be different from the front end for a C++ compiler, for example. And the backend is target machine dependent. So the backend for a ARM instruction set architecture processor is different from a backend for a MIPS instruction set architecture processor. Okay. So if you kind of see the problems in the front end, or there's a good theory behind the front end design, and most of the problems that we kind of face, algorithmic challenges that you face in the front end, they are solvable in linear time or n log n time, etc. But whereas the algorithmic problems that we face, the algorithmic challenges that we face in the backend, so they are mostly NP complete problems. Okay, so we have to. That doesn't mean the problems are unsolvable. So we have to come up with good heuristics which work for the backend. Okay. So this is the advantage of IR. Like for example, if we have a uh, if you want to design a compiler for a new programming language, so all you have to do is, like for example, if you want to design a compiler for a new programming language, okay, for this as a part of this course, let's call this language as mini C. All you have to do is you have to build a front end for this mini C programming language, uh, uh, and then generate an IR. Okay, and this IR can be passed to the backend, and the backend will automatically generate the target assembly code. So that's the advantage of using a nice intermediate representation. So in fact, that is what you will be doing in this course. You will be making use of, you will be generating what is called as an LLVM IR, and this LLVM IR will be passed to the backend of the LLVM compiler infrastructure. You can pass it to two tools. One tool is called as an LLC, which is a code generator. Okay, code generator, which generates target machine code. Okay, there is no S here. Code generator. LLC is a code generator. There is another way, so you don't need to generate code. You can just pass it to LLI. LLI is an interpreter. Okay, So in the course, this is the approach that we will be taking. For the mini C programming language, you write a front end so there are broadly two parts in that, three parts in that front end. Number one, you check for syntactic correctness. Number two, you check for semantic correctness. Number three, if the program is syntactically and semantically well formed, you generate an intermediate representation. In particular, you generate llvm intermediate representation. Once the llvm intermediate representation is generated, you can use the tools from the llvm compiler infrastructure, like for example llc. llc is a code generator which maps intermediate representation into target machine code, and lli is an interpreter which interprets the ir as it is. Okay, so this is the approach that we will be taking in this course. Okay. So the other advantage, as you can see, let's say you are designing a new processor. Like for example, in the introduction to processor architecture course, which I taught last time, so we kind of designed a mini MIPS. Okay, so we designed a processor mini MIPS. Okay. So what you do is, so now in order to take a C program and be able to run that C program on the new processor that is designed, so you don't need to do anything with the IR, you just have to build a mini MIPS backend. Okay, so you just do uh, mini MIPS backend. Sorry, mini MIPS backend. You just build a mini-MIPS backend, and this from the IR it goes to this mini-MIPS backend, and the mini-MIPS backend will generate an assembly language program which can run on the mini-MIPS processor. Okay, so that's the idea. So that means all you have, when you come up with a new processor, all you have to do is just build one backend, and automatically the source code automatically you can reuse the front ends of different programming languages. Okay, so it's a great advantage by taking this particular architectural approach in designing a compiler. Okay, so the idea, so in the absence of this particular approach, so if there are m programming languages here, and if there are n backends, if you may end up building m times n compilers, okay, for every backend front end combination. But instead, we are now having n plus n software components. Okay, m plus n software components are there. So this is the advantage. So instead of building mn compilers, you have m plus n software components, m front ends and n backends. So this is what we are aiming for. But then in practice, achieving this goal is reasonably hard, because many times when we design the IR, so some front end specific artifacts will enter into the intermediate representation, because without that, passing that information to the backend compiler infrastructure becomes difficult. So some artifacts here, some complexities here will creep into the language. Some artifacts some complexities in the scheme programming language, they kind of creep into intermediate representation. So similarly, some artifacts of backend can also creep into the intermediate representation. Okay, like for example, the intermediate representation could be dependent on whether the target machine uses an accumulator architecture or some other architecture. So like that, what happens is the intricacies of different front ends and back ends kind of creep into the intermediate representation and make that intermediate representation clunky and hard to manage. Okay, so this is a practical challenge which compiler writers in practice face. But GCC and LLVM, these are two compilers. Someone is writing on the screen. Uh, so GCC and LLVM are two compilers which are kind of successful, because the intermediate representation they use is low-level intermediate representation. Okay, so it is assembly level or low-level intermediate representation. So apparently, because of this, they are in some way they are able to handle nuances of different front ends and back ends. Okay, I will take a pause here before I move next. First is I want to see that the permissions are properly set, because someone is able to write on the screen. Disable participants annotation. And also see if you have any questions. Do you have any questions you want to ask now? Okay, I think you're all doing good. So let's move on. Okay. So, but as I said before, so generating correct code is a relatively easy task, but what is important is generating efficient code is a challenging task. Okay, so the compiler, when it wants to optimize the code generation, it wants to optimize the quality of the code it generates finally. So there are three things it will keep in mind. Number one, so the primary goal is to reduce the running time. This is what we call as the execution efficiency. 1 minute, guys. So the primary goal is reducing the running time or of the compiled code. Okay, we want the program to run fast. That is the first goal. Okay, and when you are generating code targeting embedded systems, etc., the size of the generated code also becomes an important thing. So space. And similarly, when you are generating code for embedded systems, the power consumed when the program gets executed, that also becomes important. Okay. So these are the three prime driving factors, but the dominant one is one. Most of the time, you want to optimize the execution time of the programs. Okay. So, and then second priority is space. When you are generating code for embedded systems, especially you want to see uh, what is you want to make sure that the size of the executable is manageable. Okay, so that is the second driving factor. And while doing all this, the most important thing is you have to preserve the semantics of the program. Okay, so if the semantics of the program changes, then there is no point in doing any of these optimizations. Okay, so this is the most important thing. You should preserve the semantics or the meaning of the code as you try to optimize your program. So the way it works is, so before the IR generated by the front end is passed to the back end, there is an intermediate component called as an optimizer. So actually this optimizer, it is just not one big thing. So it has multiple phases in this optimizer. Okay. So this IR passes goes through these different phases of the optimizer. Okay. And as it passes through the different phases of the optimizer, it gets better and better. Okay. Its quality gets better and better. And finally, the optimized IR is passed to the backend. Okay. So this is the structure of the compiler. So the front end of the compiler, the first thing that the compiler does is it checks for whether the program is syntactically well formed or not. Okay, so the first thing it does is what is called as syntax analysis. Okay, and the syntax analysis phase, it has two components. One is called as a lexical analyzer, and other is called as a syntax analyzer. Although it is kind of shown as no, first lexical analysis happens and syntax analysis happens, in practice that is not how things work. The syntax analysis phase kicks in and then it keeps asking lexical analysis, can you please pass me the next token? Okay, we will look into this a bit later. Okay, and once the program is syntactically well formed, then it constructs what is called as a syntax tree or an abstract syntax tree. Actually, the right word to use is it constructs what is called as an abstract syntax tree. So this abstract syntax tree is passed to the semantic analyzer, which checks for the semantic correctness of the program by doing things such as type analysis, type checking, etc. Okay. Uh, and so once the program, after if there are any semantic issues are there, the compiler generates errors or warnings. And then the abstract syntax tree is passed to the next phase, intermediate code generator. The intermediate code generator, it generates an IR form for the compiler. It generates an intermediate representation. See, this abstract syntax tree is also one form of intermediate representation, but the intermediate representation generated by the intermediate code generator, it would be different from the abstract syntax tree. Abstract syntax tree is a tree structured IR, whereas the intermediate representation generated by the intermediate code generator, it could be a linear IR. It looks like closed assembly language instructions, whereas abstract syntax tree, it's a tree structured IR. So you can see that as the program moves through different phases, initially a tree structured intermediate representation is generated. And after certain analysis on this tree structure intermediate representation, a linear IR is generated, and this linear IR is passed to machine independent code optimizer. So a bunch of optimizations will be done and these optimizations could be machine independent. Like for example, in your code, you may have something like area is equal to 2 star pi star r, but you have defined pi as somewhere here, somewhere you said hash define pi is equal to 3.14. So what happens is this area statement after compilation, it becomes 2 star 3.14 times r. So when you are, and let's say this whole thing is present in a for loop, you are computing the area of multiple times for different radiuses that you are reading from a file. So every time this for loop, every time the statement is hit, you are computing 2 times 3.4 at runtime, which takes hundreds of clock cycles because this is a floating point operation, right? So what the compiler can do is it can do a transformation called as constant folding. It can do something called as constant folding, and then change this statement into area is equal to 6.28 times r, where this 2 times 3.4 is computed at compile time itself, as against issuing an instruction at runtime to compute 2 times what is 2 times 3.4. Okay, and this optimization is completely independent of the machine. Okay, no matter what the target machine is, this optimization you can do. So these kinds of optimizations the machine independent code optimizer module will do, and then again it generates an intermediate representation, and then uh, it's the new intermediate representation is an optimized form of the IR that is passed to it. And the code generator module, it has components such as instruction selection component, register allocation, instruction scheduling, etc. Like for example, in order to do some operation, what is the right instructions you should be picking from the target instruction set architecture? And how do you allocate or assign registers to different variables? That's what the register allocation module does. And then you may want to move around the instructions a bit so that more instruction level parallelism is exposed to the target processor so that the target processor can execute more instructions per clock cycle. So like that, the code generator also does lot of stuff and generates target machine code. And then we have what is also called as machine dependent code optimizer. And then finally, target machine code gets generated. Okay. So here, if you see, uh, from here to till this point, this is the front end. Okay, till this point, this is the front end. Okay, and then you have the here middle end. Okay, middle end where different optimizations are performed, different machine independent optimizations are performed, and then the backend kicks in, and in the backend, so the optimized IR is mapped to target machine code, and not only that, certain machine dependent code optimizations will also be done in the backend. So this is the overall structure of a typical compiler. Okay, it's the same. So now let's take a look at a couple of real world compilers such as GCC. If you take GCC compiler pipeline, so for each programming language, there will be a front end. And this, what these front ends they will do is they translate this source code into an intermediate representation form called as generic. And this generic intermediate representation form is translated into another intermediate representation form called as Jimple. Okay, and this Jimple IR is passed to multiple optimization passes here. Okay, and then so after performing optimizations on this Jimple IR, what happens is you generate what is called as an RTL representation. Okay, and then again multiple optimization passes will be applied to this RTL IR, and finally the optimized assembly code will be generated. So different kinds of optimizations will be applied on different forms of IR. Okay, like for example, if you see on the Jimple intermediate representation, so you do many, you try to do loop optimizations, okay, and then there is also called what is called as code vectorization. You know, like for example, we were talking about in the last class how modern processors have SIMD units, and in order to use the SIMD units, you have to vectorize the code. Okay, and then there are many scalar optimizations will also be applied on the Jimple representation. We will study about the scalar optimizations in a different lecture down the lane. Okay, and then also interprocedural analysis. Okay, optimizations across functions will also be done at this level. Okay, like for example, if there is a function f, okay, and function and there is a loop, and in this loop you are calling some other function g. Okay, so you know, like when you call a function, there is a function called overhead, okay, to set up the stack, no, and then after the function returns you have to unwind the stack, so on and so forth. There will be some overhead. So if g is a frequently called function from f, and g could be as simple thing as get some field from some record. Okay, you are using that function for in order to make your code more structured and modular. Okay, so what the compiler can do is it can see that the number of instructions that are actually executed in G is way less than the setup code to enable the function call. Then what the compiler can do is it can inline. So let's say, sorry, so G is somewhere here. Okay, so what the function can do is, what the compiler can do is, it can replace the function call G with the actual code that is present in G. Okay, this is what is called as a function inlining optimization. So these kinds of optimizations are done on the Jimple level. Okay, these are completely machine independent. Okay, and then an RTL level. Okay, so there are many other optimizations such as register allocation, instruction scheduling. Software pipelining is also a form of instruction scheduling. So many optimizations which are machine dependent, they will be applied at the RTL level code. Okay. So now let's take the example of another compiler, Open64 compiler. So again, the important point that you should appreciate here is, so your source code, you express your algorithm in the abstractions provided by the source programming language. And then what the compiler does is it lowers these abstractions stepwise. Okay. In the first step, like for example, here, if you see, there are four kinds of four. This is level 1 IR, level 2 IR, level 3 IR, level 4 IR, level 5 IR, and finally machine code is generated. Okay, this is assembly code. So what is happening is, initially you take your source code and then you kind of come up with a high level intermediate representation. You perform certain optimizations. Okay, like for example here at the level 1 IR, so optimizations such as function inlining will be applied. Okay, and then so maybe but after that again this IR is transformed into a different form of IR, and on this IR you do certain other kinds of optimizations. Okay, maybe some loop optimizations, etc., like so on and so forth. So you keep on keep lowering the abstraction level, and at every abstraction level you try to do certain optimizations which are appropriate to apply at that abstraction level, and finally the machine code gets generated. Okay. So coming to the third example, which is LLVM compiler, which we will study in more detail in this course. So the important thing about the LLVM compiler when compared with GCC is its intermediate representation. And the key thing that you need to remember is this word called as external or persistent intermediate representation. So if you take the GCC compiler, so the GCC compiler, it no, you know, it takes the source program, generates Jimple, does optimizations on it, generates RTL, does optimizations on it, and finally generates executable code. So as a compiler writer, you may possibly take a dump of this intermediate representation onto the hard disk and see if there are any bugs, etc. Okay, beyond that, you will not be able to do much. That is, the intermediate representation of GCC, it is a main memory intermediate representation. Okay, so GCC, if you look at GCC IR, so this is a main memory data structure. Main memory data structure. So you may be possible to take a dump of it, okay, onto the hard disk. Okay, so but then you will not be able to do much with that IR beyond analyzing it visually. Okay, what is the source program and what is the IR that is being generated by the GCC. But on the contrary, if you take the LLVM compiler infrastructure, so let's say if you have a program sort.c, so the IR, so you can generate your IR in a file, okay, which can reside on hard disk. Okay, the front end can generate your IR, which can reside on the hard disk. Okay, so the extension that we use is sort.bc or sort.ll, and it is possible for you to see what this IR that is generated by the front end. Okay, so that is, and then not only that, if you want to, we can read this your LLVM middle end optimizer component called as OPT. It can take this sort.bc from the hard disk. It can optimize it, and it can again generate right back, like for example, OPT sort.bc optimized intermediate representation it can generate. And then this optimized intermediate representation, again your LLC or LLI can take them, okay? And if LLC takes it, then it will generate the assembly code. Okay, if LLC takes it, it will generate assembly code, but if LLI takes it, it interprets it directly. The most important thing here is the intermediate representation is persistent. That is, you can store the intermediate representation on the hard disk, and different modules in the compiler, different software components in the compiler infrastructure can do something with it and write it back to the hard disk. Okay, so this is an important property of the LLVM IR, that it is a external IR. It has both internal representation and it has both external representation or a persistent representation. Okay, that's number one, most important thing, uh, persistence or external representation. Number two, it is a collection of well-integrated libraries. The way the compiler is structured is the analysis passes, the optimization passes are written as a collection of libraries. Okay, so because of that, it is easy for you to make use of this analysis passes or optimization passes easily. Okay, in fact, what happens is if you look at the LLVM, the tools in the LLVM compiler infrastructure, such as compiler driver, okay, like Clang is the compiler driver, C program compiler in the LLVM compiler infrastructure. What they do is they use these uh, analysis and optimization passes that are organized as nice libraries and to get their job done. Okay, so these are the three things I want you to keep in mind. Okay, so actually first two are the important. Okay, number one, the third is an outcome of the first two. The first one is uh, an external representation for your program, an IR representation for your program. Number two, the whole compiler infrastructure is organized as a collection of libraries. Number three, there are lots of tools that are available in the LLVM compiler infrastructure. Okay, so Clang is the front end. Okay, and OPT, okay, middle end optimizer, LLC, LLI, LLDB, it's equivalent to GDB compiler, sorry, so on and so forth. There are so many tools available in the LLVM compiler infrastructure, and you can play with all these tools to get a better understanding about how the LLVM compiler infrastructure works. And then, so that knowledge will certainly help you in designing your own compiler tool, either for this course or for some other research project that you are working on. Okay, but we will revisit the discussion on LLVM compiler maybe a month later. Okay, but for the time being, this high level view of LLVM compiler infrastructure is good enough. Okay, I will take a moment here and see if you have any questions. Sritej has a question. Does the reverse backend IR to front end is possible? What makes the GCC IR a main memory data structure, as in what prevents it from being stored in the hard disk? Tanmay Sinha. So let's take the question of Sriteja first. That is, can you generate C code from the IR? Okay. So, well, it is possible, but it will not be the same C code that you would have written. Okay. Like, for example, uh, if you have some statement, let me do one thing. Let me erase all link. Okay. Like, for example, if you have a statement such as uh, x is equal to 2 star y plus z. Okay. So during the process of translating this C statement into machine code, there are many ways of doing it. Okay. So when you construct back this, like for example, you can do something like T1 is equal to 2 star y. Okay. And then no, T2 is equal to T1 plus z. X is equal to T2. Okay, these are the three statements you may generate starting from the statement x is equal to 2 star y plus z. So now constructing back x is equal to 2 star y plus z from the sequence of 3, it excuse me, it may not be exactly possible, because you could have written x is equal to z plus 2 star y, okay, or Yeah, so there are many ways of many source programs which are equivalent to the same IR. So when you do try to do the reverse, no, you don't get the exact C program that you have written. Okay. Number two, what makes the GCC IR a main memory data structure, as in what prevents it from being stored in the hard disk? Good question, Tanmay. I'm not exactly sure. See, what you can do is you can kind of dump the IR onto the hard disk and read, but you cannot construct the internal representation of it from the IR that is generated on the hard disk. I don't exactly know what are the challenges involved in reconstructing the main memory representation of the IR from the hard disk. Okay, good question. Can a Python code and C code map to the same IR? That is a question from Vaibhav Garg. So good question, Vaibhav. So there are some challenges, okay, in actually mapping Python code uh, to, it is possible, it is possible, but there are some challenges, okay, because Python is a dynamically it's a dynamically typed language, because when you say x is equal to y plus z in Python, you don't know what x, y, and z are. Okay, so y and z could be strings, or they can be integers, or there can be some other objects. So generating IR code for Python kind of languages, it's kind of hard. Okay, so in order to actually better explain uh, the question of Vaibhav. Okay, so like for example, in Python, if you have something like this, if some condition, so you have x is equal to y plus z, okay, uh, else you can have, maybe you can have here x is equal to 1, y is equal to 2, sorry, maybe, yeah, and then z is equal to 3, and here you can have y is equal to some string or some list you can have, and z is equal to some other list. Sorry, let me do one thing. This is not erase all in con slide. So let me do this. So if there is, you have a condition, okay, so if this condition is true, y is equal to 1 and z is equal to 2. If otherwise, so y is equal to some list such as a comma b, and z is another list, maybe 3 comma 4, and then here you can have something like x is equal to y plus z. Okay, the problem is in Python, when you are trying to generate an intermediate representation for the statement x is equal to y plus z, it becomes an issue, because the intermediate representation that you like to generate for x is equal to y plus z, it depends upon what is the type of the variables y and z. Okay, if y and z are integers, the IR that you want to generate would be something. If y and z are lists, then the IR that you want to generate would be something else. So because of that, generating an IR for Python kind of programming languages becomes challenging. Okay, does it make sense, Fibo? Rohan, would the IR optimizer be equivalent to a language specific optimizer in terms of producing the most optimized code? Can the IR optimizer be? I didn't quite get your question, Rohan, but IR optimizers usually they are not very language specific, but there will be some optimization passes in the IR which are kind of target some programming languages. Like for example, if the IR is generated from a C++ programming language, there could be some artifacts, because the source program is a C++ program. there could be certain kind of inefficiencies that may come up in certain segments of the IR. So you may want to introduce an optimization pass which can take care of them. But that particular optimization pass may not be useful if the IR is generated from a C program. Okay, that's a good question. Anurag Jain, can a compiled language like C or C++ be used as an interpreted language with interpreters like LL? It is quite possible. Good question, Anurag. Yeah. So that's what it is possible. You can take a C program and generate an intermediate representation, llvm IR specifically, and then just give it to LLI and it will become an interpreted language. Okay, you will lose out on performance, but yeah, it's possible. Okay, so all good questions. So let's move on now. I want to move to the second uh, yeah, I think what I will do is I have only 10 minutes. I don't want to start a new topic, but I really wanted to start a new topic. I want to give an introduction to syntax analysis in this lecture so that you can get started with uh, with your project. Okay. But I don't want to rush through at the same time. So I will take that topic uh, in the next lecture. But what I want you to do is, let me see. So I want you to start working on, let's see what I have more. I want to use a whiteboard. Okay. So what I want you to do is, so number one, so I initially said no, that we will be working on the decaf programming language. Okay, so instead of decaf, okay, so what we will do is I will ask you to define your own programming language. Okay, let's call it as mini C. Okay, this mini C, it will no have bare minimum features. Okay, like basic data types and for loop, while loop, etc. Okay, so last year, what we did is we used tools such as we used Flex and Bison. These are two tools which we use to do syntax analysis. This is what we used last year for syntax analysis. Okay, but this year, and these are based on C, C++, but this year we will be using a tool called as Antler, okay, in order to do syntax analysis. And this is based on Java. Okay, so I want you to refresh your Java fundamentals. Okay, it's not too difficult so that you can work on this project. But the advantage that you're going to get is so big because uh, the syntax analysis part, while it is relatively easy, after syntax analysis, so like the next big phase is what is called as an AST construction. AST construction, and then after AST construction, in order to do semantic analysis, okay, so you do what is called as a AST traversal. Okay, you have to traverse the tree and you have to do few things. Okay, and here we use what is called as a visitor designer pattern, in order to do this tree traversal, etc. So this AST construction, you end up writing lot of code to do this AST construction, tons of code, and also tons of code for AST traversal. Okay, so lot of code. So lot of code you write here. But by using Antler, so I figured out this AST construction is given to us. Okay, so the amount of code that we have to write, just drops down, and then also the visitor designer pattern code is also automatically given for you. So your job becomes fantastically easy and simple, and you can use the infrastructure that is generated by the Antler uh, parser generator. Antler is a parser generator. Okay, even Flex and Bison, they are parser generators. Okay, so and you can so AST construction becomes easy, the traversing the AST becomes easy, and also given that we are focusing, we are trying to restrict our attention to a small set of features which using which we can still write interesting programs. Your no, the size of your grammar will also be small. So given all this, my hope is the first three phases of your compiler construction, that is syntax analysis, AST construction, and semantic analysis, everyone should be able to do with lot of ease, okay, without putting great effort. And that's my goal. I want you to learn, but at the same time not end up spending all your time on this course itself. Okay. So I am looking forward for an exciting 1 month, the next 1 month. And today, after this lecture, no, I will post some homework 2. I will post homework 1. You should submit today. Homework 1 you should submit today. Submit it on the modules. I see some of you are submitting it on the GitHub, but please submit it on the Moodle because there is no code per se in homework 1. Homework 2, it will be released today. Okay. And then I phase 1 project will also be kicked in. Phase 1 project. Okay. And in the phase 1 project, there will be step 0. Okay. And step 0 of phase 1 project you should try to do in this week. Okay. And do again a submission of the same, commit it on the project repository by Thursday. Okay, so this is what we have, and please, if you didn't program using Java, get hold of a Java book or go through some quick tutorials online. So the programming language, like it's very similar to C++ or it's an object-oriented programming language. It makes your life very easy, and especially I'm very happy because in the past, when we were using Flex and Bison, many students used to have a problem in AST construction. You have to write a lot of code to do the AST construction. And your grammar also gets complex. People used to get they have problems in writing grammar. Many issues are there. So this time I want to see that each one of you are able to do these three phases. And but the bit of effort that you have to do is, if you are not familiar with Java, you have to catch up with that quickly. Okay. And other important thing which you will understand later is Flex and Bison. It's a parser generator which generates what are called as LR1 parsers. Okay, these are called as bottom-up parsers. Sorry, excuse me my writing. But AntLR, it's a top-down parser. It uses what is called as an LL1 parsing technique, or maybe LLK parsing technique. So the parsing approaches used by Antler and Bison are different. But let's see. So I hope you will enjoy doing the first three phases of the project. I will release all the necessary information by today's class. So put in install Antler, do the basic 101 of Antler, and then I'll also tell you what you should submit by Thursday. Okay. And in the Monday and in the Tuesday class, we will start with a new topic that is on syntax analysis. We'll start with a high level overview and then we'll get into details. Okay. Let's see, I have some questions. Could you also upload the slides as well? I think I have uploaded the slides for L1. So for today's lecture, I will upload the slides. Okay. Maybe I will upload the slides for lecture 3 also, actually. I want you to review lecture 3 slides, even though I didn't discuss them. So reviewing lecture 3 slides will help you in getting a picture on what the syntax analysis phase of the project involves, okay, and what we are trying to do with the Antler, okay. That's all I have for today. So I'd say have a great day. So if you have any questions, please stay back and ask me. Otherwise, that's it for today's lecture. Someone told the Zoom recording of the lecture is not accessible. Is it true? Can someone confirm that it's not accessible? Because when I accessed it, it is working. Okay, great. So if you have any difficulty in the course or whatever it is, don't immediately reach out for help. Drop me an email, use course model, ask questions, okay? And make the class involve, let's make it more interactive, okay? And let's help each other. Let's learn together. What is the point of Java if C or C++ can also be used with an interpreter? Okay, so good question, Anurag. Um, so first answer that is coming to my mind is uh, this LLVM compiler infrastructure. It's a recent phenomenon. Number two is I am not sure whether Java has lots of packages which makes graphical user interface design and many things very easy. But I am not sure whether all those things can be done with the same ease using C or C++. Okay. Um, so yeah, apart from that, I'm not exactly sure if there are any other issues involved in using C or C++, no, sending LLVM IR on the internet instead of Java bytecode, like, and then interpreting them. Okay, I'm not sure what issues we face in doing that. It's a very good question.